We're now going to look at Chapter 4, which is on methods for clustering. Actually, we haven't done that much in the course so far. We've just seen vectors, some examples. We know just a handful of operations on them. For example, we can look at the norm, which is a measure of size. We can look at distance between two vectors. And in fact, that's where we take off from in the idea of clustering. But we'll find that even just with this extremely small list of things we know about, in fact, in this case, specifically, only simply the distance between two vectors, we can already do interesting and useful things. So in some sense, this is just a detour out of the main topic of the course, but it's just to show you that even with an extremely small list of things you know about, we can actually do cool and useful stuff. You can use this at your next internship, by the way. And if people don't know about it, they'll be very impressed. Okay. So the idea behind clustering is this. We start with a whole bunch of n vectors. We have capital N vectors, and we're going to call them x1 through xn. That's a subscript. Notice this is a little ambiguous, right? Because x7 is actually a vector. It is the seventh vector in our list of vectors, right? So if you wanted to refer to a component of x7, for example, you might do this. And that would be, this thing here, that notation would indicate x7 is the seventh vector. This is a number now. It's the fifth entry of the seventh vector. Okay, so I have a list of vectors. And the goal is to take these capital N vectors and divide or cluster them into either partitions, groups, subsets, however you want to say it. So, for example, we might want to divide them into 3 or 5. By convention, actually, because of it's a long history, we're going to call the number of groups that we partition the vectors into k. Okay, so here's the idea. The idea is you want to make these partitions of vectors. You want to group them into groups that are close to each other. And so down here, we're going to see a picture. Here's our actual data. Now, in this case, these are two vectors, right? So we can plot them. Of course, we're not that interested in clustering 2 vectors, right? We're much more interested in clustering 10 vectors, 10,000 vectors, or even 1,000,000 vectors, right? Million vectors. And I don't know how many we've got here, maybe 100, couple hundred. It really doesn't matter, but you can see them here. Now, your eyeball tells you right away that you could cluster them into like kind of 3 groups like that, okay? That's just your eyeball. Now, of course, your eyeball is not going to work when you have vectors of dimension 10,000, right? So, but here, and it's kind of like, there's some question as to which cluster do the ones like near the between 2 lie in. But these are like detailed. The idea is just as a rough idea you get 3 groups here. Okay. So here's an example of a clustering, and what we've done is we have color coded. We have k equals 3 here, and we've color coded them so you can see which of the vectors over here have been assigned to which group. And so we have a green group, a red group, and a blue group. Okay, and you could quibble with some of our choices here. Like for example, I don't know if you can see, but there's a little green dot right there, and you might say, oh no, that one should be red. This is minor. It's not a very precise concept. It's just, and we'll see that in applications it'll be clear that it's not a very precise concept, but we'll see also it's unbelievably useful. Okay, so this is the idea. So the question is, how do we automatically come up with a clustering like the one shown here? I should add that if we're doing this for vectors that are that have dimension 2, you use your eyeball to do the clustering. You get out a pencil and you cluster them just like I did over here. That's exactly that's manual clustering. That's not going to cut it in higher dimensions. Okay. So before we talk about how to do it, I want to talk about what you might use it for. What would you use clustering for? Or what would be the setting in which you would use clustering? Well, it's actually super interesting. So here's an example. Let's suppose that the vectors are word count histograms for a collection of documents. Some people call a collection of documents a corpus. So for example, Wikipedia is sometimes considered a corpus, right? I forget how many documents, well, it's changing every day, are in Wikipedia, but that's a corpus of documents, right? And then for each document, you would have a word count histogram. It just counts the number of words. It's very unsophisticated. I want to add that means that when we associate a vector with each document, it is really profoundly stupid. It does not understand English. It does not understand syntax. It doesn't know what a sentence is. It doesn't know what a paragraph is. It has absolutely no meaning what any of the words are. It simply counts the words in our dictionary, and that's our vector. Okay, so I just emphasize how crude this really is, and yet we'll see it's pretty shocking what happens. Okay, here would be another potential area where you might do this. Is let's go back. Let's do patient clustering. So let's have a large hospital or network of hospitals, and what we do is each vector is going to represent one patient, and what it's going to have, the entries are going to encode things like age, sex, weight, height, blood pressure, diastolic, systolic, whether or not they're currently experiencing chest pain. It could give the vector could also have entries that encode whether not just symptoms, but also the results of tests. Right? Have they tested negative for something or positive for something? So that would be, or if it's a numerical test, it could. That's also that would be encoded in X. Okay, so these are your vectors. Is actually a set of attributes of each patient. Okay, now there it would be very useful if you had 100,000 patients to group them into, I don't know, I'm making this up, but 60 different clusters. And you'd probably find out some interesting stuff that way. Okay, customer market segmentation. So this is, as a matter of fact, this is done pretty much universally. And the way that works is each vector are a set of attributes that correspond to a customer. And so what you do is it would include things like their purchase history. How many dollars over the last month of item such and such have they purchased? Right, that's an example. It could include other attributes of a. It could include like where they live, age group, education level. I mean, all of these are possible, right? So we can. That's the idea. And now what you do is you would cluster these vectors, right? So. And the idea is we would get, 68 groups of clusters. And groups or clusters of customers. And then a person would get their eyeball in there and go in and look, and they'd say, oh, I see what this is. These are 18 to 22-year-old college students or something. I don't know, that kind of thing. Okay, so this would be quite useful, right? Because you could then tune your marketing and other stuff, advertising. Okay, here's an application. It's actually it's a famous one that people typically show all the time, and it's color compression of images, right? So an image here, what you do is you have an image, and what you do is you think of each of its pixels. So you might have 4 million pixels, right? In a 4K by 1K image, you'd have 4 million pixels. Each pixel is a 3 vector, which give you the R, G, and B. That's red, green, and blue intensity, right? Now, for historical reasons, those go between 0 and 255, but we'll just call them between 0 and 1. I mean, it's not going to make any difference. It's just a 3 vector, right? Okay. So if you cluster 3 vectors, it's actually super duper interesting, right? So you can actually cluster the number of different colors to maybe 100. By the way, that's not that many, right? Because these are 3 vectors. But once you get 100, you actually images that way. And then the advantage, of course, is you don't have to give 3 real numbers for every pixel. You just say, oh, that's cluster number 45. That one is cluster number 66 or something like that. And so that's kind of the idea. That's used for compression because you can describe an image way faster if you have only 100 different colors. Okay. Here's another example is in finance. So each vector corresponds to a company, and my vector includes attributes of that company. It could be, for example, the return of their stock last month. Last year, could have both of them. It could be their total capitalization. It could be their price to earnings ratio. We could encode the sector they're in, right? So for example, we could have a feature that's either 0 if you're not in the energy sector and 1 if you're in the energy sector. These are examples. Okay, so this would be So the vectors correspond to companies, basically. And now what would happen is we would take these vectors. It might be 10,000 of them, 15,000, 30,000, and they might have each, I don't know, hundreds of attributes, and then we would cluster them, right? And so this would be the idea. And so nearby vectors there mean companies that are similar in terms of the attributes. It means they're probably kind of in the same area. They have about the same capitalization, this kind of thing, right? That they're just similar. And you could use this for lots and lots of things. But in fact, what would appear when you do this kind of automatically are financial sectors, right? When you see companies that cluster together, those would be considered, that's typically called like a financial sector or something. Okay, so these are the examples. We're going to come back to the practical examples later, because what we're going to do now is we're going to talk about actually how to do clustering. Actually, it's a huge field. You can take an entire course on nothing but how to do clustering. But we're going to show you a shockingly simple algorithm that was one of the first, and it's still very widely used. Or actually variations on what I'm about to show you are actually widely used right now. Okay, so the way this is going to work, first some notation, and it's not pretty, but it's just we have to be able to describe a clustering. And so we're going to describe a clustering two different ways. One way is we're going to give we're going to take, so this is set notation. When you see that squiggly bracket, that constructs a set. And so this is a set with n elements, and the elements are the integers, 1, 2, 3, up to capital N. Those are the indices of our vectors. This symbol means that G is a subset of those, Gj. And a subset means it is, well, it's just what it sounds like. It means that it is a selection of some of the entries there. Okay, so for example, let's say we have, I'll do something really simple here. That's our, here capital N is 4, so I have 4 vectors. And then I could have 2 groups. So I would have something like this. G1 is 1 and 4, and G2 is 2 and 3. There, okay? So that's an example of a clustering. I put the first and last one together, and I put the middle 2 together, and that's my 2 groups. Okay. Now we're also going to use C sub I. So C is a vector, which is capital N long. And what we're going to do is C sub I is going to give you the group that Xi is in. So in this case, let's see. So here, C1 is going to equal 1, and C2 equals 2, right? Because this says that entry item 1 is in group 1. You can see that from here. And so C1 is 1, C2 equals 2, C3 equals 3, and C4 whoa, no, that is very wrong. This is 2, there you go, and 1, there we go, sorry. Okay, so yeah, so these are 2 ways that we'll use to describe the clusters, right? Okay, now what we're going to do is we're going to have group representatives. And so these are vectors, Z1 through Zk. Remember, we have K groups, and these vectors don't have to be in our original data. In fact, generally, they are not. They're just arbitrary n vectors, and we're going to call them the group representatives. We're going to later see what they are, and actually, they're, by the way, by themselves, going to be super interesting. But let's just they're just group representatives. Okay. Now the cluster, a very good way to actually kind of do anything is to make it an optimization problem. So the way you do that is you say, what you're going to do is you're going to write down an objective function. And in this case, we're going to write down this objective function. I will talk about it momentarily. But then the idea is we say that if this is smaller, if that objective is smaller, we like that clustering better. Okay? So you should be very suspicious of people who tell you about something and launch into a method before they tell you what it is that would make them happy. So now I'm telling you what would make us happy. What makes us happy is this J clust being small. And so that way there's no arguments, right? If you come up with another algorithm and I come up with an algorithm and we evaluate our 2 clustering objectives, then whoever is smaller is better. Their clustering is better, period. Okay? So this is kind of the approach. In fact, it's the approach for a whole lot of sort of mathematically oriented methods, and frankly, it's the correct approach, right? Otherwise, things get weird and vague, and you'd say, I don't like your clustering, it doesn't look good, and they say, yeah, well, I don't like your clustering, and so on. Anyway, so fine. All right. So let's look at this clustering. This cluster objective. So here's what it is. What it does is it iterates over all of the data, and for each vector xi, it finds the distance squared to its representative. Okay, so that's the ZCI. So this is the distance without the square. That's the distance of item I to its cluster representative. So that's how that works. And this says that we should take the sum of the squares of those things, and then we could divide by n. So you get a mean square clustering objective, right? And so this is it. So, your job here, well, here's your job. Your job is to choose the Z1 through ZK. Those are the cluster representatives. And your other job is to choose, if you like, the C's, which is the same as choosing the G's. So the C means you have to say for each item, which cluster are you in? So for item 22, are you in cluster 1, 2, 3, 4, 5, something like that. So that this is going to be your job, is to do that. Okay, so this is the clustering objective, and it's perfectly reasonable, right? Okay, so that's going to be our goal, is to choose a clustering and the representatives to minimize this number. And that's how we're going to, we'll have an algorithm that does this, and we're going to monitor our progress by looking how J cluster is it going down, has it stopped decreasing, that sort of thing. And that's also how we're going to compare two different methods. For example, if we try two different methods, or we'll two different potential clusterings, we'll judge them by this objective. Okay. So we're going to now talk about an algorithm. It's a very famous algorithm. It's actually very, very simple and yet very powerful. Okay, so here's the way it's going to work. So what we're going to do is we're going to solve the problem not all at once. Remember, our job is to find the representatives and also the assignments to clusters. Those are the CIs, right? So instead, what we're going to do is we're going to break it down and try to figure out how to do how to choose, say, the assignments if you knew the representatives, and then the converse. How would you choose the representatives if you knew the assignments? So we're going to start right now saying, suppose we knew the representatives. That's these, C1 through CK. So we're not going to mess with them. They're just fixed. And the question is, what assignment would minimize the cluster, the J cluster, right? And so the answer is actually easy to figure this out. What happens is, if you go back to the cost here, you'll see that if we look at, so Z, if I ask, like, let's consider entry I, CI appears nowhere else except that one entry. And so what it really says is, to make this as small as possible, I should choose CI to be the index corresponding to the nearest neighbor of XI in the representative set Z1 through ZK. So that's what I should do. Okay? So that's the idea. And that's it. So you'd say that this way. You will assign each vector to its nearest representative. By the way, another way to say that is, if you have not assigned a vector to its nearest Z, then in fact, by assigning it to its nearest Z, we can reduce J clust, or whatever, the cluster objective. Okay, so this makes perfect sense. It just perfect sense. Okay, now please note, this does not solve the problem. This says if you knew the representatives, the way to assign items to the clusters is to assign them to their nearest neighbor among the representatives. And again, that makes just perfect sense. Okay. Now we're going to look at the other way around. Now suppose we fix the clusters. That means every vector has been assigned to a cluster. And then the question is, how do you choose now the representatives to minimize our objective? Okay, so in this case, what we can do is, the original objective is a sum over 1 over n, but what we're going to of n items, right? But what we're going to do is we're going to rearrange them and collect all the terms together that are in each cluster. And so what it is that the cluster objective, which is the mean square distance to your representative, we're going to write it as a sum of k different numbers. And each of these pertains only to cluster J. So let's look at this notation. This says that I should sum over xi minus zj, but I'm only going to look at the I that are in gj. That means that is the items which are assigned to group J. Okay, so that's what this sum here means. And I put a 1 over n in front of it because I got that from the original one. Okay, now then the question would be this. How do you choose, let's say, for example, zj? Well, zj only affects one of these, which is j sub j, right? And then it's this thing. And so we're left with the question, how do you, if I give you a set of vectors, namely the xi's that are in partition J, in GJ, group J, then the question is, how do you choose a single number that minimizes the mean squared distance to them? Now that has a very simple very simple solution, which, in the book we describe how to work it out or whatever, and it's completely intuitive. It's the mean. In other words, if someone says, how do you find a vector that minimizes the mean squared distance to a set of other vectors? You simply average all those vectors, and that's the solution of that problem. Okay, so that says Zj is literally, the representative is the average of the vectors in its group. Again, this is completely natural. Now, I want to point out that at this point, we have absolutely not solved the problem because we've been asked to optimize over both the partition and the representatives. Now, all we know how to do, but at least we know how to do two things pretty well. If you fix the representatives, we know how to choose the clustering. If we know the clustering, we know how to choose the representatives. And now we're into something very famous in mathematics, algorithmic mathematics anyway, when you can't really solve the problem, but you can do you know how to solve part of it if one thing is fixed, and the converse, right? And that's just called iteration. It's pretty dumb, and that brings us to a very famous algorithm. It's called kmeans. It's actually from the 60s. But like a lot of things, when you start looking, the history goes back older than that, and the ideas were certainly there. All right, so here's the way it's going to work. It's very simple. We're going to alternate between updating the partition. That means literally assign each item to its cluster. You assign each item to the cluster which corresponding to the closest representative. Okay? Then we're going to update the representatives. And to do that, that's simple. For each group, we are going to we're going to set the representative to be the average of that group. Okay? That's a famous algorithm. And in fact, what happens is in every single step, our objective goes down. That's good because it makes us happy when our objective is small. And the reason is pretty clear, right? That in the first step, when I assign each element, if I move an element, if an element had been in group 3, if a vector had been in group 3 and I move it to group 6 because the group 6 centroid is closer, my objective is going to go down. Same for the other part, the second step, that if I update the representatives by assigning them to be the mean, once again, the objective goes down. Okay, so here's the algorithm. Here's how we're going to write it. It says that we should simply update the partition. So you find the nearest neighbor, and then you update the centroids. And what will happen is at some point, you're going to get to the point where the partition doesn't change, and thereafter nothing will ever happen. Right? That's it. In other words, every item is assigned to its nearest neighbor among the representatives, number one. And number two, each centroid is the average of its entries, the entries in its group. Okay? Each representative or centroid. I should say that the centroid here is an alternate name for the representative or mean. Okay. So, and then when it stops, we quit. If the partition is the same on two, if the partition doesn't update, then there's nothing to do, and we quit because nothing's ever going to change again. So that's the k-means algorithm, very famous algorithm. Oh, and notice that to understand this, you only need to know a very little bit. You know what a vector is, and you know what distance between two vectors is. I mean, it's not much. Okay. Now, let's see. As I said, the objective goes down every step until they stop changing. right? Now, one thing about this is that you might think this would actually solve the problem. Okay, so now the fact is it does not. We will even see specific examples where the algorithm stops and it is not the optimal clustering. Optimal clustering means that clustering, there's no clustering that has, and choice of representatives that has a lower objective. And we'll see that that's just not the case. So it doesn't actually solve the problem. And so when you have an algorithm that's not guaranteed to really fully, completely solve your problem, it's called a heuristic, okay? There's many heuristics around. I mean, honestly, it's obviously better to have an algorithm that solves something exactly. I mean, of course, because then you don't have to worry about it. There's no worry. But there are many, many cases where basically we can't do that, and so we resort to heuristics. And heuristics can be extremely powerful, and this is one of the cases where it works very, very well. Okay. Okay, so one fact about that is, for example, depending on how you initialize the algorithm, right? You initialize it either with some representatives or with an assignment of items to clusters. Depending on how you do that, that can actually affect the final result. Okay, and what people do sometimes is they run k-means like 10 times, let's say, with different initializations. They let it converge. And then among those 10, they just choose the one that has the lowest value of j clust, because that's kind of what we're after. Okay, so that's the idea. But it has to be remembered that depending on how you initialize it, you can get different clusterings. Okay, so that's just the way this works. Okay, we're going to look at an example now. The first one's going to be an abstract example. In fact, it's the example we started with at the beginning of the lecture. And so what we're going to do is we're going to take this data. Now, of course, this data is two vectors, and the right way to cluster two vectors is with your eyeball and draw. Okay, but we're just going to see we're going to walk through k-means and see what it does in this case. Okay, so here we go. So we initialize it with these cluster representatives. Okay, I don't know why, but we did. Okay, there's just three different vectors: the red, the blue, and the green square. Okay, then what's happened here is I have colored the points according to their nearest neighbor among those three. So if you're a green point, like all these guys are green down here, they're green because they are closer to the green centroid or representative than the red or the blue. And up here, it's just sad. It's very sad. There's just 2 points that are closest to the red representative than the blue or green. Okay, now the next step you'll recall is we now update the centroids. And what that means is, or the representatives, that means that among all of these green ones here, we're going to calculate the average, and that's going to be our updated representative for greens. And look, eyeball there, something in the center. Okay, it's like right there. Okay, well, okay, here's where it is exactly. Okay, so that's the updated green centroid. Okay, or representative. All right. The blue is going to shift over to here, and you can see that blue thing is kind of in the center of where the blue things are. And okay, it's kind of pathetic. There's 2 points, and the average of the two is a point right smack in the middle. And so this sad little red box here is telling us it is now the average of its two constituents. Okay, that's iteration 1. If you look at that is a pretty bad clustering right there. But the point is we're going to iterate. So that's iteration 1. Let's look at iteration 2. On the next step, things are getting a little more reasonable, because now what we do is we go back, and for every data point, we fix the new centroids, which are here, here, and here. And we now go back and we ask every point, which one are you nearest? And then that's your color, or that's your assignment, group assignment, and that we do that. And now you see, well, we got a big old group down here. We got a few more reds. And then we update the centers. And so now these update this way, and we keep going. Okay, so this is iteration 3. Here's iteration 10, and you can see we're getting there, right? So by now, still a bit wrong, right? You can see that these green things morally should be blue, and so on. This little bottom down here morally should be red. And by morally, I'm just joking. It means like our eyeball can see what the clustering is. And but if you go like up to iteration 15, the thing just stops, and that's the final clustering you get, right? And so there it is. And you might quibble with it. You might say, oh, that green point maybe should be red. Whatever, fine. The point is, that this is the final clustering. Now, of course, this was just to walk you through what it looks like, how k-means works. Obviously, the point of k-means is not to cluster two vectors, because you can do that with your eyeball and a pencil. Okay, so that's not the point. The point is this algorithm works in dimension 10, and it works in dimension 100 or 1,000 or 1,000,000, right? If Amazon clusters their customers, there's a whole lot of customers and a whole lot of items that they may have bought last month, right? So, these are very, very big problems, and basically the exact same algorithm just runs. Okay, so that's that. Okay, all right. Let's look at how this algorithm converges as a function of iterations. Well, this is jclust, and remember the whole point of having an objective is so we know when we're happy or not, right? So on the first step it goes down, it kind of makes some little baby progress, and all of a sudden, woo, it goes down here, and then this ends up being our final clustering objective, and it's about whatever it is. It's about I don't know, 0.3, 0.35, I don't know. So that's how k-means ran on this thing, and this is actually kind of typical.